All right, and we are live. Hello, everyone. My name is Jeffress, and I am a developer advocate at Meta for PyTorch. And today we are coming at you with the PyTorch 2.0 Q&A following the PyTorch conference that took place in December of last year. So today's topic is TorchMultiModal, and I have two special guests on with me today. We have Evan and we have Ankita. So Evan, please give yourself, please give the audience an introduction. Let them know who you are.
Sure. Yeah, thanks, Justin. Hi, my name is Evan Smothers. I am an engineer working on TorchMultiModal. I have been at Meta for about 3 years now.
Cool. All right. And we also have Ankita on the line. Ankita, please introduce yourself.
Hi, I'm Ankita Day, and I'm an engineer on the PyTorch multimodal team. And we've been working on this project for about a year, and we just had a beta release last year.
Great, yeah, and we'll definitely be diving deeper into Torch Multimodal. But one thing I also just wanted to call out, unfortunately, we also had another person on the call. His name was Kartikay, sorry. And unfortunately, due to a personal issue, he had to bow out of today's session. So unfortunately, he can't join us today, but looking forward to having him on in future streams. So yeah, thank you. Anyway, let's keep moving forward. So just want to call out that this is also part of a multi-part series. So there'll be another episode coming on March 1st, and I will share a link to that and where you sign up at the end of the stream. So yeah, so now that we have all of the housekeeping items out of the way, just want to start getting into the topic. So Evan, what is multimodal AI?
Yes, so I guess at a high level, multimodal AI would be any task that's dealing with multiple input data types. So it could be text, images, videos, audio. There's other examples too, but those are like the primary ones that we would expect to see.
Cool. And so you have these audio and text things that you're sort of combining. How as a developer, why should I care? Okay, great, I've got these different texts and audio. What is why should I be interested?
Yeah, that's a good question. So I think in some cases, okay, there's NLP is a well-studied field, computer vision is a well-studied field. There are very sophisticated models, state-of-the-art models for all of these things that you can learn embeddings, you can learn these lower dimensional representations of unstructured data, right? But oftentimes the world is multimodal, right? So the way that you or I process what we see on a daily basis, we're taking in many different types of inputs, right? Like auditory, visual, etc. And we're processing those jointly, right? We're not dealing with each one individually. And so there are a lot of cases in the real world where I think self-driving cars would be one good example. You have sensors attached to self-driving cars, and those are picking up maybe your inertia or other physical properties of the vehicle, and then also maybe visual data around. And you need to process those jointly in real time to make decisions, right? So just like what we do all the time. And so processing each one individually is not necessarily always going to give you the same richness of information that you would get if you learn these joint representations over the different input types.
Yeah, so I think one of the things that is interesting about it, it's AI is, especially neural nets are sort of mimicking, human, I wouldn't say behaviors, but human abilities to be able to make decisions in a less defined, rote way from traditional programming. And so I kind of think of multimodalities as that layering upon layering of senses, right? So it's we have five senses, six senses, five senses. I kid, but it's like layering those together helps your brain to sort of filter out different information, and so that multimodalness helps sort of mimic yet another further. It's like combining those different like senses together. So it's like giving a sense or senses to work with your model and training.
Yeah, definitely.
Great. So what are some of the common applications that people would use like multimodal or before we get into Torch multimodal, but just multimodal in general?
So I mentioned self-driving cars. That's like maybe a bit more exotic from like the stuff that we are looking at. But more traditional stuff would be like content understanding. So say you're looking at social media content, right? And you have a post, whether it be on Twitter, Facebook, Instagram, TikTok, what have you. There's often text, maybe multiple channels of text, right? It could be a caption on the post. It could be hashtags. It could be the text that they like embed on the video. I forget what that's called. And then you have maybe one or more images, one or more videos, audio streams from the video, and you want to represent that, and then so derive some meaningful representation, and then ultimately you'll use that representation to for many different downstream applications. So it could be like ranking the content that you see, making recommendations. It could be like integrity applications, so making sure that you're not showing like offensive or harmful content. Those are just a few. There are like countless applications, but those are a few examples.
Great. Yeah. And so, if somebody was wanting to get started with Torch multimodal, actually, let me take a step back before I ask that question. Just want to make sure that people who are watching, like this is, the Q&A. So if you have questions, feel free to ask them in the chat. And, I'm monitoring the chat on YouTube and on LinkedIn. So for those of you who are viewing the different spaces, like I am monitoring both chats. And so I will find a good place to ask your questions. So please, don't be shy and feel free to ask away. So Evan, if like somebody wants to get started and they're new to multimodal AI, how would they get started, and in particular, how would they get started with Torch multimodal?
Yeah, I think we provide different levels of abstraction to kind of get into the library. Depending on what you want to do, like let's say you just want to tinker around and you have no idea what you're doing yet, but oh, hey, I saw this model, I like this model, I'd like to learn more about it. So we'll provide like APIs where you can just import a model, say with pre-trained weights, with a single line of code, just some builder function that will allow you to import state-of-the-art models from research very easily. But maybe if you're an ML practitioner, like just the model class alone is not enough to solve the problems that you want to solve, right? There's a lot more that goes into it beyond that. So what's your data set? How do you iterate over it? Maybe you have multiple data sets. What tasks do you have? How do you set up your training loop? All of that. That honestly is where like a lot of the time can get spent, right? And so if you want to even forego all of that, then we give some example scripts where you can actually just run some command from the command line, and you can either train on a task or a set of tasks. You can maybe fine tune for like some specific tasks, which we can talk about more later, or you can like evaluate models. And all of these are documented in READMEs, and we have some like example notebooks that you can also play around with to get started. So those are like easy, nice, user-friendly ways to just like get familiar, see what's out there, see what the options are, and start tinkering. That's really what we want people to do. So
great. Yeah, and I believe you and Ankita put together some slides to cover some of the main points you want to dive into regarding Torch Vision. So are you ready to jump into that now?
Yeah, let's do it.
All right, great. Oops, here we go.
Okay, so I'll share my screen. Okay, so we're talking about Torch multimodal, and we want to power innovation in multimodal AI. So we can kind of jump around here. Like this is obviously like a more open-ended, flexible format, so I don't want it to be like too regimented, but the high-level agenda is like what are the basics of multimodal AI? What does it mean? Why do we care about it? We already covered some of that, so we don't need to go too deep into it. Then let's talk, obviously, about Torch Multimodal, what we provide, why we structure things the way we structure things, what our goals are, and then finally we can do some deep dives. So we have a few different notebooks that we can walk through, just how some of what I was mentioning before, how you can import different components, how you would use them, how you would set up maybe a training loop, a fine-tuning loop, what have you. Okay, so some of these we covered, like content understanding, integrity classifiers, self-driving cars. We covered a lot of the real-life applications, but some of the stuff that maybe I didn't mention would be like research tasks, and a lot of these you'll see in our library. So visual question answering is a big one. Text-to-image retrieval, text-to-video retrieval, text-to-image generation. These are all pretty common multimodal research tasks. So these are the things that, you know, if you want to know why should I care about multimodal AI, like these are the tasks that you can use it to solve. So you can train some model that will learn representations over text, image, video, audio, and then you can use it for these like exciting applications. So on this slide, we give like an example. This is visual question answering. And here you can see an image of a sunset, I guess. I don't know if it's a sunset or a sunrise, but, and a natural language prompt, right? So the question is, what is the color of the sky? And we want to answer that question just using this like raw unstructured data. And to do that, we have to learn representations of both the text and the image, right? If we just learn representations of the image in a vacuum, we won't really have like a notion of what it means to be blue or red or what it would look like if we see that in an image. And we can get into more details of like how this is actually done. But in this case, we have like two labels, right? So we're kind of implicitly like treating this as a classification problem.
Yeah, and it's interesting because as you were talking, I was just kind of thinking like if someone was listening to this presentation without, you know, like say they were listening to this while they're driving or running or something, and they're not really watching the video, and you're talking about that question, you know, what is the color of the sky? Like what ultimately are they going to think? They're probably going to think blue, right? Like that's like the common, like, oh, what's the color of the sky? Well, it's blue, but you know, that's outside of context. And, you know, I imagine some people will think, you know, in their default in their mind is blue. Some people might default to gray, especially if you live up in the Pacific Northwest like I do. And, you know, and some people might say, you know, it's pink, you know, if it's sunset, right? But like, you know, it's pretty interesting. It's like this multimodality discussion. It's like, you have to know not only the you know, the question that was asked, but the context, and that image that you're looking at here gives you that extra bit of context needed to tell like, okay, what is the color of the sky? It's blue. If you were just asking a question and answer prompt, like blue would probably be, you know, a high majority of what people would expect the answer to be.
Yeah, exactly. So you need to learn kind of, you have some prior, but if your prior is based only on, yeah, like a limited set of information, right? So having, like you said, having the full context is very important. Yeah, I think another good example of what you're describing, actually, I mean, this is maybe not so academic, but is memes, right? Like you have a meme and it's an image with some text over it. And depending on what the background image is, like if I use the same set of text over like the Drake meme versus like the Galaxy Brain meme, it has a totally different meaning, right? And only by understanding both of those inputs together, like in a joint fashion, can we really like discern, okay, hey, this meme is making a joke, or this meme is saying something mean, or is, yeah. So yeah, memes are another good example of that, I think. Okay, so yeah, I think I mentioned some of the tasks here. Yeah, generation is another big one that's kind of been very popular lately. That's really taking off. So that's like another very exciting area in multimodality, right? And we list text to image, but of course there's other ones too. I've seen, I think even like text to audio. There's, yeah, so that's like a very exciting field as well. Okay, so hopefully this slide and our discussion so far, everyone who's watching is saying, "Oh, multimodality is so exciting! Like, I really want to use these models, use these techniques, and all these tasks are like very interesting. I'd like to, apply models to solve them." So our goal is to make that easier for people. TorchMultiModal is a PyTorch domain library, and our goal is to accelerate innovation in the field of multimodal AI, make it easier for researchers to work with multimodal models, make it easier for ML practitioners or ML engineers to, either put those models into production, scale up those models. We just want to reduce the friction in this kind of overall flow. And there are like a few different ways that we can do that. So these are some of our like main principles here. First is modularity. So we want to provide like good building blocks. So these would maybe be like lower level components. One thing that's worth calling out about multimodal AI is, like I mentioned, like computer vision, NLP, these are active research fields in their own right, like very active research fields. And often multimodal models will take a state-of-the-art computer vision model just as one encoder, right? So these are big models. So we have a state-of-the-art vision encoder, a state-of-the-art text encoder, and then we also want to fuse them. So these are large models. They're complex. They're often quite custom. And we want to make it easier for people to be able to kind of like plug and play. So I have maybe some implementation from a research paper, but I want to swap it out. I have a different text encoder that I like more, right? We want to make it easy for you to do that. So we provide a lot of encoders, fusion modules, losses, layers, stuff like that, to allow users to, plug things in as they wish and tinker around, right? The other piece is interoperability. So the idea here is to provide sort of a rich ecosystem that users can leverage. So, computer vision has its own set of tools, techniques, libraries. NLP has its own set. They don't always play nicely together, right? So we want to make it easy for people to use components from these different libraries in the PyTorch ecosystem. So if I have like a ResNet from Torch Vision and I want to plug that in and I want to use it as an image encoder in some multimodal model to do visual question answering, then we can make that easy to do. And if I have maybe a model from a research paper that's a little bit custom and it has, I don't know, 100 million parameters in it, but I want to scale it up. I want, to train a model with billions of parameters. We want to make it easy to do that using like PyTorch distributed APIs. So we want nice integration with all of these things for our users. And then finally, extensibility. So I kind of referenced like some of the tasks that we apply multimodal models to. And one of our goals is to provide task agnostic core models. So you could think like one example would be, we have Flava in our library. And this is, a few different encoders and some losses. And we want to provide a model that isn't necessarily custom tailored to a specific task so that the user can then take that core component and build upon it. So if the user has their own data set or task that they want to use, then they can easily import our models, tack like a head on top of it for their specific task that they're working on, and be good to go, right? So those are kind of the three principles. You can also look at some of the things that we provide. So I mentioned some of the low-level components, like encoders, fusion modules, different layers, losses, transforms. This is, again, for like a more customizable experience. So if you already kind of like are familiar with the field, you know what you're looking for, and you want to maybe do something like a bit more custom, then you can use these. You can import them and piece them together how you want. Think of them like Lego blocks. At a slightly higher level, we have full end-to-end models. So I mentioned before, you can write one line of code, import a state-of-the-art model from research with pre-trained weights. And you can also tinker with that as well. Like there is some flexibility there too. So if you want to swap out, one of the encoders, swap out the fusion module, like that's all stuff that we support. And then finally, the example scripts, we can get more into those in detail in some of the demos, but yeah, we offer scripts for pre-training, fine-tuning, evaluation. And also this just shows, like, if you're maybe not as familiar with this side of things, like, hey, how do I actually like hook up a data set? How do I find the right optimizer? How do I run a training loop? Yeah, how do I do all of these things? Especially with multimodality, like a lot of the complexities in the data set, like you'll often have these like really large JSON files with very rich like annotations that can be like pretty cumbersome to work with. And if you're new to the field, like you can spend a lot of time there, an inordinate amount of time there. And so we want to at least give you a starting point. Obviously, we can't cover all use cases, but show you, hey, here's how you would do something like this, and make sure that it will run out of the box. And then you can tinker with it and like write your own script if you have your own data set to plug in. So I can give a couple examples of each of these three things. So for building blocks, we have vector quantized VAE. This is useful for learning discrete latent representations of data. It's used in a lot of generation models as like a visual, as a tokenizer for the visual component. Contrastive loss with temperature. This is something from CLIP, which was published by OpenAI a couple of years ago. And this is essentially you're computing the similarity between image embeddings and text embeddings. You're just taking the dot product and then doing like some cross entropy. But there's this additional parameter that can be learned as well. And another thing worth calling out with the contrastive loss is this can actually be kind of annoying if you are doing distributed training. You have to maybe like gather your embeddings from a bunch of different GPUs, and it's like non-obvious how to put them together and how to actually compute the similarity. We do all that for you, so you don't have to worry about any of that. Yeah, for end-to-end models, we have CLIP, which I mentioned. We have embeddor, which is a multimodal object detector, which comes from, it's based on DETR, which is another popular computer vision model. And then we have some example scripts like Omnivore, which was published by FAIR. We have a pre-training script for that. Omnivore can be used to learn generic embeddings that can be learned for like image input data, video input data, and 3D images as well. And then Flavor, we also have Zeroshot scripts and fine-tuning scripts for that. And that we can go into in more detail as well. And on the right-hand side here, yeah, this is an example from embeddor. So embeddor will do object detection anchored on phrases in the text, right? So we have a question, what color is the hat on the person next to the man carrying the suitcase? And these are actual predictions from the model with probabilities. You can see it detecting the suitcase, the hat, and the person. And we have a notebook as well that can go through that in more detail. Let's see. Yeah, actually, let me pause here and jump to the embeddor notebook quickly.
Yeah, and while you're doing that, we had a question come up in the chat from on YouTube, and someone asked, how do you extract the joint representation for the multimodalities? And they said, do you learn a mapping between representations of modalities? I figured this is a good place to ask this because you're jumping into the Jupyter notebook. So yeah, how does one extract that representation?
Yeah, I think this is the perfect place to ask it. Yeah, so we have this handy architecture diagram right here to walk us through it, I think. So you can see basically up to this concat block here, everything to the left of that, each modality is being operated on independently. Okay. So a CNN for the image. So I think this is like a ResNet that they're using. And then they're projecting into like a common embedding space. And down here, yeah, you have a text encoder, Roberta, doing the same thing. And eventually you have, yeah, these embeddings. I think they're represented in terms of, the text is represented in terms of tokens. The image is also represented in terms of tokens. And you can concatenate them along the token dimension. So now instead of like, 500 text tokens and 200 image tokens, you have 700 tokens, let's say. And that's just some new matrix or a tensor or whatever. you concatenate them, and then you pass them through a transformer. And if you know, with transformers, you can use masking to determine which weights attend to which other ones. And so you allow the image weights to attend to the text weights. And that's how you're fusing them here, is through a transformer. So basically, by doing that, you're learning the joint representation through the transformer. That's just one example. There are a bunch of different ways to do it. So whenever I'm talking about like fusion modules, that's what I mean. It's the fusion module is where you will learn the joint representation typically. Yeah.
So to add to that, I think there are also some examples in academia where you have the entire encoder being shared between different modalities. So Omnivore is one such case where image, video, and 3D data is all being processed by the same encoder itself. So there is no fusion module. All the modalities go into the same sort of trunk. So that's also a place where like people are moving towards more early fusion sort of architectures.
Yeah, that's a very good point. Okay, we can take other questions too. If not, I'll jump back into the notebook. So yeah, that's some summary of what is happening in Embeddor. So we can look at the input data would be an image and a text, a caption for the image. And yeah, each gets passed through the unimodal encoders and then fused. There's a lot of other stuff happening here actually, but we can kind of like gloss over some of the details here. Like I mentioned, they get fused through a transformer in this case, and Embeddor and Deader, which it kind of inherits from, treat object detection as a set prediction problem. So it actually predicts a set of boxes. If you're from like a computer vision background, you're familiar with other cases where maybe you have to use all these heuristics for pruning or merging boxes or stuff like that. Embeddor is a little bit different. It just predicts a set, and then it determines an optimal matching between the predicted boxes and the ground truth boxes. So if that sounded like gibberish, then it doesn't matter too much. Ultimately, what we can see in the output here is we have a bunch of bounding boxes, and they're actually like anchored to phrases in the text, right? So we can see the orange box maps to a cat, right? And the purple boxes map to the paws, green box maps to the fence. And so each of these is a prediction with some probability. If you go back here, you can kind of see the analogy with this image. So we can give an example of like how you would use Embeddor in TorchMultiModal. I mentioned previously that you can import one of these models with a single line of code, and that's this here. So here we have a model class. This is the easiest entry point. It's already built. It's using the ResNet backbone. And if we want to like tinker with some of the parameters here, we can do it. So we can also just change the number of queries, which is one of the parameters that determines how many bounding boxes we want to predict. We can maybe change the dimension, the transformer, stuff like that. So there are like some modifications that can be made even within just that single line pre-built model. If we want to get a little more sophisticated, the builder function is just an instantiation of this class. So here's the class. And the class is built up of a bunch of different components. So this is a state-of-the-art model. It's fairly complex. So in addition to the image backbone, the text encoder, and the multimodal transformer, which are all the three components here, 1, 2, 3. There are a bunch of other things, positional embeddings, projections, other embeddings. So all of these get used to build up the model class. And here I give kind of all the defaults. This would be used to build the model from the builder function. So 2D positional embedding, projections, 2D convolution, stuff like this, an MLP, a linear layer, and all of those get fed into the model class. So it's composed of lower level components. So that will give us the original model from the builder function, just in a more complicated way. But the point is, by going to this like lower level of abstraction, we get more control, right? So up here we have the Roberta model. Let's say, oh, I want to try using Distilbert from Hugging Face, Hugging Face's implementation of Distilbert. I can do that. I can load it here, and I'll just pass it into my text encoder argument in the model. Okay, so new text encoder. I want to change my class embedding from a linear layer to an MLP. Okay, done. So it's pretty easy to like experiment with these things, plug them in, swap them out, and see what you get, right? We can also look at how to apply it on a task. So Embeddr is used for a handful of different tasks. There's phrase grounding, visual question answering, which we talked about before, a few other ones. Let's talk about phrase grounding. So if we go back up to the original image, the idea here is to associate like a noun phrase. So basically these highlighted portions of text with, could be one or more bounding boxes in the image. And there's some subtlety there that we can, again, gloss over. But the point is actually the way Embeddr is trained, you can evaluate the pre-trained model directly on this task without having to do any fine tuning. As opposed to other tasks like visual question answering, you do have to fine tune the model. So here, just like with the original model class, we also provide a kind of single line builder function, right? So we want to apply Embeddr to a task. We use this task-specific builder. And then we can load the checkpoint from S3 and put the model in eval mode because we're not doing any training here. And then we can download a few images. That's all that's happening here. So yeah, this notebook should be runnable for anyone. It's in our repo. So if you want to try it out, this is just like a rendered version of it. But in theory, all of this should be runnable if you want to like just go through it and like see how it works. So we load the images.
Yes, and just to chime in, I did share the link to this notebook in the chat, so you should be able to follow along. And then there was also a follow-up question to the one that you answered previously about the mapping of the different modalities. And the person from YouTube asked, is the fusion model quicker than separate models?
Is it quicker? Probably not, because it's more, right? It's more compute to fuse the embeddings, but it's not quicker, but it's more effective is what I would say. I don't know. Ankita, do you have any thoughts on that?
Yeah, I think it depends on what you mean by quicker. So say you're just doing a concatenation, which is sort of like the base case, right? You're just getting to unimodal encodings and doing a concat. That is pretty cheap, right? Versus you have a full-blown transformer, in which case you're now sort of training 3 encoders together, right? Assuming you are also training the unimodal ones. If you're freezing them, then again, it's lesser cost. So it depends on like case basis, yeah.
Mm-hmm. Yeah.
Great. Thanks. And then there's another question, but I think I'll wait to ask until you've finished going through this notebook.
Sure. Yeah, that sounds good. Yeah, so we loaded a few images. We also loaded, like I mentioned, these JSON files. So we loaded these annotations as well. I think it's a fairly large file. Oh no, maybe this is just a demo one. So this is nice and small, so you don't have to worry about that. And then we create the dataset class. So this is also one thing to call out is we have like our core library, which is all built nightly and importable via all the usual means. We also have an examples directory. So that's where a lot of our like example scripts and dataset utilities and stuff like that will live. So the very highest level entry point that I was mentioning before with like end-to-end examples, you'll be looking in our example script, and then there will be subdirectories for each state-of-the-art model. So we have one for Flava, one for Embeddr, one for Omnivore. There are a few others too. So we import the dataset class. We create the transform. So we have an image transform here, which is just transforms from Torch Vision. We have a tokenizer here, which we're getting from Hugging Face. And then we create the data set. An astute observer may notice we're not actually using the transforms here, which looks a little funky, but it's because we're actually like going to plot things and do some custom stuff. So we're not going to plug it right into the data set. We want more control and can apply the tokenizer and image transform as we wish instead of having the data set do it for us. There's a lot of plotting utilities. I won't get too much into the details of these, but I think the meat of it is probably right here. We have this function plot inference results, takes in an image, takes in a text. It's just using the model that we already built and the transform and tokenizer that we already built. And it will tokenize the text inputs, so convert them to like a sequence of integers, transform the image, feed them into the model, and then the model will return some outputs, which I think should be some data class containing like embeddings of logits embeddings and some other stuff. And then we'll do some post-processing so that we can display the image. And the post-processing is basically, yeah, that's up here. We're taking a softmax, we're throwing out some low confidence boxes. And then I think we also need to like remap using the tokenizer. So it will return basically a sequence of tokens in the text, and we'll convert that to text instead of just integer values. But we'll gloss over a lot of that. So here's an example from the data set. It's an image of a couple dancing outside a cafe, a guy is singing, there's a bunch of tables, and the caption says, "A couple is ballroom dancing in an open room." This is the caption from the data set. So we can call this method plot inference results, and it will show us the different entities in the image. So here it shows an open room is basically the whole image. It shows a couple, gives us a couple different bounding boxes with different levels of confidence. I think one is even hidden here. And yeah, this is one thing about Embeddr is it will return like multiple bounding boxes for the same entity sometimes. And that's, again, in the details of the paper. But we can also, so the reason that we decoupled the transform is because we can also pass in whatever we want. So we can ask Embeddr to detect different objects in the image beyond just what's in the original data set. So I was just tinkering around. I saw a couple lanterns in the background. Can it detect the lanterns? So I pass in 2 lanterns for the text. And it can, you can see them back here. You can pass in a backpack and a blue railing, just picking up other random objects in the image. And the backpack is pretty well hidden, but it detects it with very high confidence. Same with the blue railing. Singer with a microphone. I had a harder time with that. I thought that the woman dancing was a singer, but I guess you can't get everything right. And yeah, so there's a lot more in here, actually. We have other images. We have visual question answering further down. But I think I'll hit pause on this, see if we have any questions. And if not, I'll jump back to some other material.
Yeah, someone on LinkedIn asked, for the multimodal calibration, if there are 2 different sensors, for example, like a LiDAR or an RGB, and it says even images can be generated by projection of the LiDAR, and they cannot align perfectly. So let's say the ground of truth is in the RGB images, like if they offset the CMS. So is there a way to improve the fusion results? And would that to be used like an attention module? Like, so that's
a good question. That has me stumped. I don't know. I guess calibration is sort of a different beast. So we want to calibrate the RGB inputs to the LiDAR inputs.
Yes. Yes.
I see. Okay, I'm sure that there are techniques, but I'm not familiar with any personally. That's like a bit outside my domain, I would say.
Sure. Yes. So yeah, unfortunately, Ankita, do you have any other insights or things that you can share? Or if not, we can move on to another question.
Yeah, I think it's very use case specific. So what we tried to do, and we haven't looked into sensor data yet, and that's probably on our like very future roadmap. But like we sort of try to provide tools that people can just sort of experiment with. So like there are say 3 fusion modules, you experiment with 3 of them and then sort of empirically figure out which one works the best. Of course, there are some like sort of intuitions on what would work better for say text plus image versus say image plus video kind of thing. So there might be something like that specifically for the LiDAR domain, but generally the idea is you can do it empirically.
Great. So we had another question from LinkedIn. It's a comment and a question. So they say, this is a great initiative for making multimodal models easy to work with. It would be great to create a chart or have a chart specifying the hardware requirements needed for training and inference. So yeah, is there any sort of thing out there that shows that information?
Yeah, that's a very good question. I think that's even like broader than multimodality, because scaling models, and I mean, okay, it depends on what you're talking about. If you're talking about like memory, making sure that a model can fit into memory and that you can train it successfully, that's one thing. So in that case, like that's a very general problem, and there are heuristics for doing that. I think actually we have like, maybe I can jump over to this blog post that we were talking about previously. Here, this is a blog post that was released by Ankita and Kartikay and some folks from PyTorch Distributed. And here they're talking about basically scaling up Flava to larger model sizes. And they do show some heuristics for how you can determine, okay, here's how much model can fit in this many GPUs of this type, right? So I think they were doing like 8 A140 gig GPUs. Yeah. And I think using like traditional techniques like data parallelism and stuff like that, they could get up to maybe just under 1 billion. And then after that, you have to use more sophisticated things. But I guess the answer is like, my answer is it depends on many different factors, right? The GPUs you're using, the model size, the batch size, all of these things will like, yeah, be factors in any model scaling. So yeah, it's complicated, but I agree, a chart would be nice.
Okay. And then one last question, and then we can move on. This comes from LinkedIn. Can these models, these multimodal models, be trained using fully sharded data parallel? Like, is there interoperability between these two different PyTorch features?
Ankita, do you want to take this one? This is a good question.
Yes, I think the blog says it all. Yes, we are fully compatible with DDP, FSDP. We also try to be up to date with any of the new like features coming out of PyTorch distributed. So even though FSDP at that time, I think it was beta, not sure now, we sort of have examples to show how you could just like compose things, mix and match with FSDP, even the activation checkpointing wrapper that they have.
Great.
Yeah, and I would add, those are even in our repo. I think there are configs for Flava at different model sizes. So in this table above, I think we have like I don't know if we have the 10 billion config. We definitely have like the 4 billion config. So these are all under, I think, our examples directory, right? There are different configs, and you can see some of them use DDP, some of them use FSDP, and then, as Ankita mentioned, some of them have activation checkpointing turned on or off, and there are other optimizations that are made as well.
All right, great. And LinkedIn says this is amazing in all caps. So I think they're excited. It's safe to say. Awesome. All right, just a quick time check. We have about like 17 minutes left. So I know we've got a lot more to cover. So, and I want you all to be able to cover it. And so yeah, let's keep moving forward.
That sounds good. Yeah, I'll call it on the embeddor material for now. Like I said, it's on the GitHub page, and I think Justin has shared the link. So thank you, Justin. Yeah, we can jump back to our slides here. So I think we covered this pretty well, but we can also look at some other examples. So the embeddor example was just pure inference, right? It's nice. We have all these nice images and plots that we can do, but ultimately, sometimes you just want to train a model. So we can show you how you could do something like that. So here's Clip, which is a model from OpenAI, published a couple of years ago. We talked about it a little bit already. This is another kind of like late fusion model, right? We pass text through a text encoder, we pass images through an image encoder, and then the way that we fuse them is we compute the similarity between the embeddings. Well, we project them to a common space and then compute the similarity between the embeddings. And yeah, this performs very, very well, and it like really took off for, I think, like zero-shot image detection was the thing people were most excited about. So we have a lot of the components from Clip in our library, and we'll just go through like a quick example of how you could set them up. So the three main things would be like the dataset transform for converting raw text and images to maybe tensors, right? Because that's what we need for our model. Second would be the model. So here I think we're using, there are a few different versions of Clip. This one is using the VIT large. So this is just the image encoder, is Vision Transformer large. And this is, again, one of our builder functions. And then finally is the loss. So we mentioned this on the previous slide, contrastive loss with temperature. Yeah, so that's what we'll use to actually compute the loss once we get the similarity between the image and text embeddings. And then it's pretty simple, actually. So we just instantiate the transform. Here we have a data set, whatever your data set may be. And we just pass the transform into the data set, and then we wrap it in a data loader to iterate over the data set. And we set the batch size. Here we set it to be 16. But for Clip, it's important if we really were training Clip from scratch, like we want a very large batch size, right? As large as possible. That becomes important for the model performance. Okay, we instantiate the model. Again, just using this builder function, single line of code. I think we have a flag for pre-trained weights now. If not, we were working on that. So, and then we define the loss, and we set up the optimizer. I guess one thing usually the optimizer gets glossed over. One thing worth saying here is usually you would just use it for model.parameters, but because of this temperature parameter and the loss, we also need to make sure that we include the loss parameter, right? Because we also want to update that parameter as we train the model. Okay, and then we just write a nice little for loop. So this is just a toy example, but we iterate over the batches in our data loader. We take the image and text from the batch. So batch will just return the tuple image text of tensors. And then we feed it through the model. So we'll get image embeddings and text embeddings out of the model, pass it through the loss, and then do the usual like backward weight update, all of that good stuff. And that's it. Easy. You can train Clip now. Yeah, so we also have a demo for Flava. Maybe I can do, I mentioned Zeroshot before, so maybe I can go through some Zeroshot example here. So actually, I guess first, before I do it, let's look at this architecture a little more. So Flava is a model that was released by FAIR, I think, last year. And it's trained using multitasking over multimodal and unimodal objectives, and both supervised and unsupervised. So it's kind of like the kitchen sink. I mean, you can see the different losses here, these L sub MIM, L sub GC. So these are the different losses that it's trained on. This would be like masked image modeling, masked language modeling, contrastive loss, like we were talking about with Clip. And then there are some other ones in here as well. So this is Flava's architecture. It's using, yeah, I think it's like transformers all the way down. So you have vision transformer for an image encoder, vision transformer for a text encoder, and then a multimodal encoder that's like a smaller version of that. So let's see how we can use it. This is a little different than the previous notebook. The previous one I just rendered. This is just a collab notebook. And I think we have
it looks like the collab needs permissions to be viewed.
Oh, okay. Wait, does it mean you see it in the stream at least?
You can see it on the stream, yes. But if you click on the link and you're on like your personal Gmail, it might not. I viewed it from my personal. It said that I needed to request access.
Okay, we can work on that, but yeah, I think we can work on giving people access to that. For now, we can just go through what we have here. So here we want to show how you can use Flava for zero-shot image classification. Again, this is just like a small toy example, just to give you the flavor of how this kind of stuff works. So here we want to, again, define our data set transforms. Probably are noticing a pattern, right? We need to process the data, and we need to feed it through the model. And then we need to maybe do something with that, maybe something task specific, or maybe just visualize it or whatever. So here we get our transforms from Torch Vision. It's that nice interoperability that we were talking about, right? And we just compose a bunch of standard image transforms. And then we also have a text transform, which is from BERT. So this is using like the BERT tokenizer. And this is actually in our library. And then we import the model, again, model builder. Here we have a pre-trained model key, so this will tell us which weights we want to load. And so for zero-shot image classification, we just want to put the model in eval mode. Again, we're not training anything, we're not updating any weights. So we'll put it in eval mode and we'll put it in no grad mode down here. And then we're just loading a sample image, pizza.jpg, aptly named because yeah, that's the image that we are trying to classify. And if you're not familiar, in zero-shot image classification, the idea is we're classifying something that is possibly unseen in our previous label set. So we don't have any like prior information about what the labels could be. So that's why actually here we're just creating the labels. And so we pass house, pizza, and dog, but we can pass anything. So it doesn't matter. And the reason we can pass anything is because we're just feeding these through the text encoder, right? So whatever candidate label we have, we'll give it to the text encoder. The text encoder will learn an embedding. And then we'll use the similarity of that embedding with the embedding of the pizza to try and predict what it is. And so then we just take the image, pass it through the transform, take the texts. So we're taking 3 different labels here and we're feeding them through the transform. And then we're padding them to a fixed length. And then we use the model to encode the image into some embeddings, encode the text into some embeddings. You can see we're doing projection equals true. So we want to compute the similarity. So we need to make sure that we're in the same embedding space. So we're projecting these to a shared embedding space. And then we're taking the CLS token here too. And then the similarity is just the dot product between image embeddings and text embeddings. So now this will give us scores for the similarity between the pizza image and each of the candidate text labels that we have, the 3 of them. And we need to convert it to probabilities first. So we take a softmax, and then we just take like the argmax, and that will tell us what our prediction is. And I think down here, after all the embeddings, you can see, yeah, so here are our final predictions. These are the probabilities. So I think the first one was, what was it? Dog, pizza, and house. And the pizza is the one with the highest probability. So we predict pizza. So this is just an example of how you can use Flava for zero-shot image classification. Yeah, can pause there.
Great, thanks. Yeah, we're just so everyone tuning in, we're trying to figure out the best way to get the Google Colab links made public for you. So unfortunately, we were unable to share that at this time for you to follow through. So follow along, but we'll figure out a way how to share that. And then somebody asked if we're going to share the slides. I'm actually not quite sure what we're doing with slides. You know, the person expressed that it's kind of hard to see it, and would like to view it higher resolution. So apologies for that. I'm not exactly sure if we've been making the slides available. I know that, like, you know, there are some like post follow-up emails that go out for those of you who signed up through Bevy and stuff. And I don't know if those emails include the slides, but I'll look into seeing like if we are sharing slides, where those are. So yes, thanks for your questions. Great, yeah, and we're at about 7 minutes, so I think yeah, just keep moving forward. I know we've still got a little bit more to cover.
Sounds good. Yeah. Yeah, I think we're nearing the end of this journey anyways. So we covered Flava. And I think really the next thing is like what's next on our radar here. So we can jump to that. So we want to continue to increase the support for different modalities that we have. Right now, we're in beta. So we're still iterating, we're still figuring things out, we're still making our APIs a little bit more stable. So that's one thing we definitely want to do, is soup up our APIs, especially around like handling image and text data, because that's the one that's the most canonical for a lot of the models that we have. We do have other stuff in there. We have video. I mentioned Omnivore with 3D images. So, but the image and text APIs are the ones we really want to stabilize those, because that's a lot of the bread and butter. And then we really want to expand into other state-of-the-art research models. I mean, multimodality is such a broad field. We are barely scratching the surface at this stage. So dealing with audio data, dealing with sensor data, which Ankita mentioned previously, like these are things that we're looking at for the future. So that's one thing. Second would be, like self-supervised and semi-supervised learning. I think like masked autoencoders are becoming a very big thing now. There was that paper, like masked autoencoders are scalable vision learners. That was a huge paper. And so that's really been like taking off. And we have some version of that in some of our models, right? I mentioned Flava is doing masking, and so that's self-supervised, like masked language modeling, masked image modeling. But we want to make those, again, make those APIs more stable, make them more plug and play, and show that you can apply them to kind of a broad set of models beyond just, right now, okay, it's a component of one of the state-of-the-art models, but we want to make it so any user who wants to train on one of these self-supervised tasks can just do it with like an easy import and make it pretty frictionless. And then finally, new tasks. So I mentioned visual question answering. We have some generation, some retrieval, the phrase grounding demo. So we have a fair number of tasks in our example scripts already, but we want to keep building out that suite as well. So a couple here would be like, cross-modal translation, multimodal summarization, and more generation. So those are all the areas that we're looking at. I think one other thing that's like not mentioned on here, but since we were talking about it, scaling up models. So we scaled up Flava to 10 billion parameters using FSDP and activation checkpointing and various PyTorch distributed bells and whistles. I think we want to integrate that more tightly with all of our models and just make it easier and make it self-serve for people who really want to take a state-of-the-art model, scale it up, and have like a really smooth experience with that. And then this is just a bunch of resources. If people are interested, obviously our repo, we would really love to get people to come in, try it out, break things, open issues, create feature requests, any of that. Like we're very open to all of that. We're definitely looking for feedback. So would love to hear people's thoughts on the library. And it's a good opportunity to influence the direction that we're taking the library in.
Yeah, for those of you tuning in, I will post the link to all of these resources that are on this slide into the chat, so you don't have to look at each character and type them into your browser. So don't worry about that. So that'll be coming in a second. Before we wrap, I have a couple other questions. I know earlier we talked about FSDP and how TorchMultiModal supports that. But I was wondering, like, if there are other, like, and I think Ankita, you might be the best to answer this question, but like, how does TorchMultiModal fit in with other PyTorch domain libraries like Torch Visions and Torch Text?
Yeah, that's a good question. So basically, Torch Vision, Torch Text, all of these domain libraries are being developed by our sister team. So when we started out, our goal was to reuse as much as possible. So a lot of our models do reuse unimodal encoders from the respective libraries. There are times where like there are just like slight variations on top of the standard unimodal encoder, like clip VIT is an example, which is somewhat different. Like there's one layer norm extra compared to the standard VIT. So for such cases, we do implement our unimodal encoders, but generally we try to reuse. And also, like if you want to sort of compose, say, Torch Vision encoder with like a fusion module, you should totally be able to do maybe a bit of wrapper logic here and there to make sure the data formats match.
Great. Yeah, and that answers somebody else's question that was in the chat about using Fusion. So that was good. And then, I was wondering, like, can I use my own like custom data sets? And if so, how would I use that? with Torch Multimodal?
Yeah, so like at a high level, we expose like model and transform APIs. So say you're using the same task as the pre-training code of the model, then you can just get in your data set and plug and play, right? And that can be any data set, can be a Hugging Face data set, or from your own custom one. If you're trying to use another task which is outside of what the model was pre-trained on, we also give the lower level code trunk API. So you could just import the trunk, tack on your own head, like task specific head, and write a bit of like transformation, data wrangling logic to get it in the format that our transforms require it. And then you can start using just the trunk and any of the custom logic that you have for your new task.
Great. Let's see, we're almost at time. Let's see, I think you talked about some of the future plans. But is there any other things that you'd like to share or sort of hint at? If not, that's okay.
Not too much at this time. Yeah, like new modalities, self-supervised, semi-supervised learning, new tasks, scaling. We are also looking at like improving performance of models, like from an efficiency perspective. But yeah, those are like the broad strokes, and hopefully can give more details soon.
Great. Let me finish posting this into the chat before we sign off. So I just shared the links to, well, hopefully it didn't cut that URL in half. But I just shared the links in the chat on YouTube, and now I have to go over to LinkedIn and just share those out. So I want to do that just before we sign off, so that way it's attached to this. One last. Okay, can I just grab this out of here? Okay, here, let me just copy and paste. All right, great. So those are those resources. They're available now on LinkedIn. You don't have to squint and hurt your eyes looking at the links on the slide. So you'll just click and access those. So great. So thank you all for tuning in. We're at time. Thank you all for your questions. Thanks for being active and amazing members of the community. And I also want to say thank you, Evan and Ankita, for being here today to talk about Torch Multimodal.
Yeah, thank you. It was a pleasure.
All right.
Thank you.
Thank you so much.